Hello, in this lecture I answer two questions. The first question, you find out the area of this green shape. The second question, you find out the area of this square ABCD using three different methods. So we'll start with the first question. In the drawing, we have a circle that is inscribed by this triangle ABC. So triangle ABC blocks this circle. In addition, we know that AB, side AB of triangle ABC equals to 6 units in its length, side AC equals to 7 units in its length, side BC equals to 9 units in its length. Again, on the test, let's find out the area of this green shape. So first of all, we define angle ACB. This angle is theta. And we will implement the law of cosines. This triangle ABC. So, let's click on the law of cosines. The law of cosines is true for any triangle. This is triangle ABC, that could be any triangle. Side AB equals to A units in its length, side AC equals to B units in its length, side BC equals to C units in its length. Angle BAC, this angle is equal to theta degrees in its size. So in this triangle ABC, that could be any triangle, the following equation is true. That cosine theta equals to A squared plus B squared minus 2 times A times B. Again, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So, we will implement the law of cosines. This triangle ABC. According to the law of cosines, the following equation is true, that cosine theta equals to 7 squared plus 9 squared minus 6 squared over 2 times 7 times 9. So I write it down. Triangle ABC, according to the law of cosines, the following equation is true. Cosine theta equals to 7 squared plus 9 squared minus 6 squared over 2 times 7 times 9. And again, in the right triangle, in triangle ABC, according to the law of cosines, the following equation is true. Cosine theta equals to 7 squared plus 9 squared minus 6 squared over 2 times 7 times 9. Seven squared is 49 plus 6 squared is 63 plus 9 plus 8 squared is 81 minus 6 squared is 36 divided by 7 times 9 is 63 and 63 times 2 is 126. So the derivative of this expression we have 49 plus 81 is 130 minus 36 over 126. 130 minus 36 is 94 over 126. And 94 over 126 is equal to 0.7169. So in total, we should find out that cosine theta equals to 0.7169. I would like to find the value of theta itself. In order to find out the value of angle theta, we operate the opposite function of cosine, that is our cosine, on the result of cosine theta, that is 0.7169. This way we get the value of theta itself. So our cosine, that is the opposite function of cosine, of the result of cosine theta, that is actually 0.7169, is equal to angle theta itself. And our cosine 0.7169 is equal to theta, and our cosine 0.7169 is equal to 40.368 degrees equals to theta. So theta equals to 40.368 degrees in its size. So 180 degrees minus theta equals to 180 degrees minus 40.638, that is actually 139.632. So if we're going to find out that 180 degrees minus theta equals to 139.632 degrees, in the next step, when we find the center of this circle, this point is point O. When we find the point of tendency of tangent BC with this circle, this point is point L. When we find the point of tendency of tangent AD with this circle, this point is point Q. And we define the point of tendency of tangent. We define the point of tendency of tangent AC with this circle. This point is point P. We define the radius of this circle as R, and we join points O and M together by straight line. Point O in the center of the circle, point L is the point of the circle itself. Actually, point L is the point of tendency of tangent BC with this circle. So point L is the point of the circle itself. Therefore, OL is the radius of this circle is equal to R according to our definition. The radius OL is equal to R. The radius OL is drawn to point L, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius LO according to rule 1. If BC is perpendicular to LO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. We join points O and P together by straight line. OP is of course the radius of the circle is equals to R according to our definition. According to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. The next step, we define line segment BL as A. That is to say, line segment BL equals to A units according to our definition. BC equals to 9, AL equals to A, and therefore LC must be equal to BC minus BL, that is 9 minus A. So BC equals to 9 minus A units in its length. Here we can implement rule 2 in our drawing. So, repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common start point to a circle are equal. In the drawing, we have a circle. This is the common start point, point P. From the common start point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So you can implement rule 2 in our drawing. This is the common start point, point B. From this common start point, point B, we have two tangents to this circle, tangent BN and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BN equals to BQ. But BN is A according to our definition, therefore BQ must be also equal to A units in its length, but they are equal to each other according to rule 2. AB equals to 6, BQ equals to A, and therefore the missing line segment AQ must be equal to AB minus BQ, that is 6 minus A. The next step, and focus this common solid point A. From the common solid point A, we have two tangents to this circle, tangent AQ and tangent AP. And the following for all two, they are equal to each other. That is to say, AQ equals to AP. But AQ is 6 minus A, and therefore AP must be also equal to 6 minus A units in its length, according to all two, of course. In the next step, we focus on this common external point C. From the common external point C, we have two tangents to this circle, tangent CL and tangent CP. And according to all two, they are equal to each other. That is to say, CL equals to CP. But CL is 9 minus A, therefore CP must be also equal to 9 minus A, according to all two. AC, side AC of target ABC is equal to 7 units in its length, according to what is given us the question. But AC consists of two line segments, AP plus PC. So AC equals to AP plus PC, AP plus PC. AC equals to AP plus PC. That is to say, AC equals to AP is 6 minus A plus PC. PC is 9 minus A. So in total, AC equals to 6 minus A plus 9 minus A. So AC equals to 6 plus 9 is 15. Minus A is minus 2A. So in total, AC equals to 15 minus 2A. AC is 7, so substitute AC by 7. And we get that 7 equals to 15 minus 2A. Here we subtract 7 and also relate 2A to this equation simultaneously. We get that 2A equals to 15 minus 7 is 8. So 2A equals to 8. Here we'll divide this equation by 2. So we get that A equals to 8 over 2 is 4. A equals to 4 units in its length. 6 minus A is 6 minus 4, that is 2. 6 minus A is 2. 9 minus A is 9 minus 4, that is 5. Here 9 minus A is 5. This is quadrangle OPCL. But again, this is quadrangle OPCL. We know that the sum of the angles in any quadrilateral is equal to 360 degrees. Repeat again, the sum of the angles in any quadrilateral is equal to 360 degrees. So the sum of the angles in quadrilateral OPCL equals to 360 degrees. So which angles we have inside quadrilateral OPCL? 90 degrees plus 90 degrees, it is 180 degrees. This is angle theta, so plus angle theta, plus the missing angle LOP. In total, the sum of those four angles inside quadrilateral OPCL must be equal to 360 degrees according to the rule that I mentioned. split again. The sum of the angles in quadrangle OPCL equals to 306 degrees. And that is to say 180 degrees plus theta plus the missing angle LOP. In total, they must be equal to 360 degrees. Here, we subtract 180 degrees from this equation. So we get that theta plus the missing angle LOP is equal to 360 degrees minus 180 degrees is 180 degrees. So in total, if you found out that theta plus the missing angle LOP equals to 180 degrees. Here we'll subtract theta from this equation. We get that the missing angle LOP is equal to 180 degrees minus theta so actually this is the missing angle LOP. This is the missing angle LOP. Is equals to 180 degrees minus theta. But we already found out that 180 degrees minus theta equals to 139.632 degrees. Okay. I don't know that 180 this equals to 180 degrees minus theta equals to 139.632 degrees in its size. In the next step, we'll find out the area of this triangle ABC, according to a special formula. Okay, the area of triangle ABC is equal to the square root of S times S minus A times S minus B times S minus C. A, B, and C are the side lengths of this triangle ABC, that is to say, it is 6, 7, and 9. So, those are the side lengths of triangle ABC. S is the semi-perimeter of this triangle ABC. The semi-perimeter of any triangle is equal to the perimeter over 2. Again, the semi-perimeter of any triangle is equal to the perimeter over 2. The perimeter is the sum of the lengths of the three sides. So the semi-perimeter of this triangle ABC equals to 6 plus 7 plus 9 over 2. Okay, again, the semi-perimeter of this triangle ABC equals to 6 plus 7 plus 9, that is the perimeter over 2. S is the abbreviation for the semi-perimeter. for the semi-perimeter S of triangle ABC is equal to the perimeter. It's actually 6 plus 7 plus 9 over 2. 6 plus 7 is 13. 13 plus 9 is 22. 22 over 2 is 11. So if you found out that the semi-perimeter of this triangle ABC, the semi-perimeter S equals to 11 units in its length. In the next step, we find out the area of this triangle ABC according to the formula that I presented to you. The area of triangle ABC according to the formula that I presented to you is equal to the square root of S times S minus A times S minus B times S minus C. S, the semi-perimeter S equals to 11. AB and C are the side lengths of triangle ABC. A is 6. B equals to 7 and C equals to 9. So the area of triangle ABC according to this special formula is equal to the square root of S is 11, the semi-perimeter, times S minus A. S is 11, A is 6, S minus A is 11 minus 6, that is 5, times S minus B. S is 11, B is 7, so S minus B is 11 minus 7, that is 4, times S minus C. S is 11, C is 9, so S minus C is 11 minus 9, that is 2. The square root of 4 is 2. Yeah, the square root of 4 is 2. So we take out 4 from this root and get that area of triangle ABC is equal to the square root of 4, that is 2. Side root we left only with 11 times 5 times 2. So in total, the area of triangle ABC is equal to 2 times square root of 11 times 5 times 2. 11 times 5 is 55, and 55 times 2 is 110. So inside the root we left only with 110. So the area of triangle ABC is equal to 2 times, side root we left with 110. The area of triangle ABC equals to 2 times the square root of 110, so it's in its size. Actually, any triangle that blocks a circle, like this triangle ABC that blocks this circle, we have a special formula for the area of any triangle that blocks a circle. Actually, the area of any triangle that blocks a circle is equal to S times R. S is the semi-perimeter of the triangle. In our case, the semi-perimeter is 11. R is the radius of the circle that is inscribed by triangle ABC. So R is the radius of this circle that is inscribed by this triangle ABC. So R is the missing variable. So the R times ABC equals to S times R. We already found out that the R times ABC equals to 2 times square root of 110, square root in size. So the area of triangle ABC is equal to 2 times square root of 110. So in total, we found out that 2 times square root of 110 is equal to 11 times R. Here we will divide this equation by 11 and finally get that the radius R of this circle that is inscribed by triangle ABC is equal to 2 times square root of 110 over 11. And 2 times square root of 110 over 11 is equal to 1.907. So in total, we found out that the radius R of this circle that is inscribed by triangle ABC is equal to 1.907 units in its length. This is sector OPL. Okay, then this is sector OPL. What is a sector? A sector is a portion of a circle enclosed by 2 radii and the arc PL between them. Okay, again. The green shape AOB is a sector. This sector is a portion of this circle enclosed by 2 radii and arc AB between them. And those 2 radii of the circle are defined as the legs of this sector. So angle theta is located between the legs of this sector, and the area of this sector AOB is equal to pi r squared. That is the area of this circle that contains the sector times the angle between the legs of this circle, that is theta, over 360 degrees. Okay, again, the area of this sector AOB is equal to pi r squared. That is the area of the circle that contains the sector times the angle between the legs of the sector that is theta, over 360 degrees. Our task is to find out the area of this green shape. So what is the area of the green shape? For the drawing, it is very easy to see that the area of this green shape is equal to the area of quadrangle POLC, this quadrangle POLC, minus the area of this sector, sector POL. And again, the area of this region equals to the area of quadrangle POLC, minus the area of this sector POL. So the area of the green shape is equal to the area of this big quadrangle POLC minus the area of this sector POL. Okay, again, the area of the green shape, that is the area that we are looking for in this question, equal to the area of quadrangle POLC minus the area of sector POL. The rounded line around POL is a sign for a sector. This sector POL. In the next step, we join points O and C together by straight line. Okay, again, we join points O and C together by straight line. By joining points O and C, we have two right angles. Right angle OPC and right angle OLP. Right angle OLC. Actually, quadrangle POLC consists of those two right angles, and therefore the area of quadrangle POLC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, the area of quadrangle POLC must be equal to the area of the first shape, that is the right angle OPC, plus the area of the second shape that it consists of, that is the right angle OLC. And again, the area of quadrangle POLC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of the first shape, that is the right angle OPC, plus the area of the second shape, that is right angle OLC. So the area of the green shape equals to the area of quadrangle POLC minus the area of sector POL. What is the area of the sector POL? According to the formula that I presented to you, the area of sector POL must be equal to pi r squared, that is the area of the circle that contains the sector, r is the radius of the circle, times the angle between the legs of the circle, that is, so the two legs, times the angle between the legs of this sector, that is 139.632 degrees, over 360 degrees. And again, in total, the sector POL is equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 139.632 32 degrees over 360 degrees. What is the of this right triangle and OPC? Actually, we know that the area of any triangle equals to the base of the triangle times the height over 2. We take the base as OP, the height is PC over 2. So the area of this right triangle OPC equals to OP, the base OP times the height PC over 2. And again, the area of the right triangle OPC equals to the base OP times the height PC over 2. And what is the area of this right triangle OLC? The area of this right triangle OLC must be equal to the base OL times the height LC over 2. Again, the area of this right triangle OLC is equal to the base OL times the height LC over 2. Again, the area of the right triangle OLC is equal to the base OL times the height LC over 2. Now is the area of this sector POL. So we found out that the area of sector POL equals to pi r squared times 139.632 degrees or 360 degrees. So what is the radius of this circle? R. So we found out that R equals to 1.907 units in Islam. So substitute R, here, this expression by 1.907, and we get that the area of sector POL in total equals to pi times r squared. R is 9.07. Again, R is 1.907, and therefore r squared is 9.107 squared times 139.632 over 360 degrees. So in total, the area of sector POL equals to pi times 1.907 squared times 139 degrees, 149.632 degrees or 360 degrees. So what is the value of OP? OP equals to R times PC. PC equals to 5 divided by 2. So in total, we should find out that the area of this right triangle OPC is equal to 5R over 2. Plus the area of this triangle OLC is equal to OL. OL is R times LC. LC is 5. over 2. So in total, if we found out that the area of triangle OLC is equal to 5R over 2 minus the area of structure POL. The area of structure POL equals to pi times 1.907 squared times 139.632 degrees over 360 degrees. Actually, the value of this expression in total is equal to 4.387 square inches in size. The area of this sector POL is equal to 4.387 square inches in size. So the area of the green shape in total equals to 5R over 2 plus 5R over 2. 5R over 2 plus 5R over 2 is 5R. Minus the area of sector POL, that is equal to 4.387 square inches in size. R equals to 1.907, and therefore 5R must be equal to 5 times 1.907. That's actually 9.535 minus 1.387. So in total, the area of the green shape equals to 9.535 minus 4.387 square inches in size. And 9.535 minus 4.387 is equal to 5.148 square inches in size. So if we found out that the area of the green shape, that is the area that we are looking for this question, is equal to 5.148 square inches in size. Okay, again, the area of this green shape, the area of this green shape, that is the area that we are looking for in this question, is equal to 5.148 square inches in size. So we finish with the first question. In the next step, I'll present you with the second question, and we'll solve the second question by using 3 different methods. The second question, our task is to find out the area of this square ABCD. So in the drawing, we have square ABCD. This is diagonal DB. This is again BDP. This is equals to 30 degrees in its size. This is line segment BP or side BP. This is equals to 5 units in its length. This is again PBC, that is equal to 30 degrees in its size. Again, our task is to find out the area of this square ABCD. know that the diagonal of a square bisects the angles of the square. So diagonal DB bisects angle ABC, and diagonal DB bisects also this angle ADC. All the angles of the square, each angle equals to 90 degrees. Diagonal DB bisects angle ABC, therefore the first half, this is the first half, is equal to 90 degrees over 2 is 45 degrees. And this is the second half, is also equal to 45 degrees in size. But this angle equals to 13 degrees, and therefore the missing angle must be equal to 15 degrees in size, because the second half equals to 45 degrees, and 15 plus 30 is 45 degrees. So the missing angle here must be equal to 15 degrees in its size. Likewise, diagonal BD bisects angle ADC. So this is the first half, is equals to 45 degrees in its size. And this is the second half. This is the second half. It is also equal to 45 degrees in size. But this again close to 30 degrees, and therefore the missing angle must be equal to 15 degrees in its size. 30 plus 15 is 45. That is the size of the second half. In the next step, we will do a construction. That is to say, from point C, we will draw angle bisector of this angle DCB. Again, from the vertex C, we draw angle bisector of this angle DCB. So, this is an angle bisector, and therefore bisect angle DCB into two halves. The first half is 45 degrees, and this second half is also 45 degrees in its size. In the next step, we'll extend line 7DP until it touches the angle bisector. And we will define the touching point of the extended side DP with this angle bisector. This point is point Q. When doing this construction, we can triangle DCQ. This is triangle DCQ. In triangle DCQ, this angle equals to 45 degrees, this angle equals to 15 degrees. 45 degrees plus 15 degrees is 60 degrees, and therefore this missing angle must be equal to 120 degrees in its size. according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So the missing angle, the first missing angle must be equal to 120 degrees in its size. In the next step, we will join points B and Q together by a straight line. By joining points B and Q, can then triangle BQC. This is triangle BQC. So, in the next step, we prove that those two triangles can go into each other according to side angle side rule. That is to say, we prove that triangle BCQ, this triangle BCQ can go into this triangle DCQ according to side angle side rule. So we have to prove that this is triangle BQC and went to this triangle DQC according to side angle side rule. So all those two triangles can go into each other. First of all, side BC or triangle BQC is equal to side DC or triangle DQC. BC equals to DC. You know that all the sides of square ABCD are equal to each other, and therefore side BC equals to side CD because they are both the sides of square ABCD. Again, side BC of triangle BQC is equal to side DC of triangle DQC. They are both the sides of a square, therefore they are equal to each other. In addition, those two angles are both equal to 45 degrees and therefore they are equal to each other. So this is again BCQ. Or triangle BQC, and it is equal to this angle. This is actually angle DCQ. Or triangle QDC. Repeat again. Angle BCQ of triangle BQC is equal to angle DCQ of triangle DQC. They are both equal to 45 degrees and therefore they are equal to each other. And finally, QC is the common side that belongs to both triangles. So I can write down that QC equals to itself as a common side that belongs to both triangles. So I actually found out that those two sides and the angle that is included between those two sides in this triangle BQC are correspondingly equal to those two sides and the angle that is included between those two sides in triangle DCQ. And therefore, those two triangles can run to each other according to side angle side rule. We have those two sides and the angle that is included between those two sides in triangle BQC. This triangle BQC are corresponding equal to those two sides and the angle that is included between those two sides in this triangle DQC and BQC. And therefore, those two triangles can run to each other according to side angle side rule. So triangle BCQ congruent. This is the same congruent to triangle DQC according to side angle side rule. And for the part that those two triangles can go into each other, we know that those two angles also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other in their sizes. So this is again CDQ. And it is equal to this angle, this is a triangle QBC. And triangle BQC. And again, CDQ triangle BQC and triangle DQC is equal to triangle QBC triangle BQC. But we already found out that this is again CDQ is equal to 15 degrees in its side. So you can write here that angle CDQ equals to 15 degrees. And for this equation, 15 equals to angle CDQ equals to angle QBC. We derive that angle QBC is also equal to 15 degrees in its size. So actually, this is again QBC is equal to 15 degrees in its size. Diagonal DB bisect angle ABC. Divide angle ABC into two halves. The first half is 45 degrees and the second half is also 45 degrees. So this is the second half. This is equal to 45 degrees in size. So 15 degrees plus 15 degrees is 30 degrees, and therefore this missing angle must be equal to 15 degrees in its size, because 15 times 3 is 45 degrees. That is the size of the second half of angle ABC. So the missing angle must be equal to 15 degrees in its size. In the next step, we focus on this triangle DBP. This is triangle DBP. So on copy triangle DBP, and we will implement rule 8 that talks about an external angle. This triangle, triangle BDP. So actually, this is triangle DBP, the point for the original drawing. All the angles inside triangle DBP are defined as triangles. This is angle BPQ that is located outside triangle DBP, and therefore it is defined as an external angle. Again, angle BPQ is an external angle. The question is, what is the size of the external angle BPD? What is the size of angle BPD? That is an external angle. Again, what is the size of angle BPQ? This is an external angle of triangle BPD. Rule 8 answers on the question. That is to say, rule 8 determines the size of an external angle of a triangle. So I'll read rule 8 and we'll implement rule 8 in our drawing on triangle DBP. This way we find out they have this external angle BPD. So I can click on rule 8. According to rule 8, an external angle of a triangle is equal to the sum of the two interangles that are not adjacent to it. In the drawing we have triangle ABC. In triangle ABC we have angles alpha, beta and gamma that are defined as interangles. This is angle E that is located outside triangle ABC, and therefore it is defined as an external angle. And the size of this external angle E, according to this rule 8, is equal to the sum of the two interangles that are not adjacent to it. This is angle gamma. Angle gamma is definitely adjacent to angle E. The two other interangles that are not adjacent to angle E are those two angles, alpha and beta. According to this rule, the size of angle E is equal to the sum of the two interangles that are not adjacent to it. That is to say, it is equal to alpha plus beta. So the external angle E equals to alpha plus beta. Okay, implement rule 8 in our drawing. Now, drawing, we have, this is the external angle BPQ. According to rule 8, the size of the external angle BPQ equals to the sum of the two interangles that are not adjacent to it. This is angle VPB, definitely adjacent to angle VPQ. The two other angles that are not adjacent to angle VPQ are those two angles. And according to 8, the size of the triangles, it is equal to the sum of the two triangles that are not adjacent to it. 30 to 8 is equal to 15 degrees plus 30 degrees. 15 degrees plus 30 degrees. 15 degrees plus 30 degrees is 45 degrees. So in total, I should find out the size of the external angle BPQ is equal to 45 degrees. Angle BPQ equals to 45 degrees in its size. This is angle BPQ equals to 45 degrees in size according to rule 8. So in the next step, we'll focus on this triangle BPQ. In triangle BPQ, this angle equals to 15 degrees. This angle equals to 45 degrees. 45 degrees plus 15 degrees is 60 degrees. And this third angle must be equal to 120 degrees in its size. According to the rule, it said that the sum of the angles in an triangle is equal to 180 degrees. In the next step, we will prove that triangle BCQ, this is triangle BCQ, can point to triangle BPQ. And again, and prove that those two triangles can point to each other according to angle side angle rule. So I have to prove the triangle BCQ, this is triangle BCQ, it corresponds to this triangle BQP. So why those two triangles can go into each other? First of all, those two angles are both equal to 45 degrees and therefore they are equal to each other. So here this is angle PCQ. The triangle BCQ and this is equal to this angle. This is actually angle BPQ. This triangle BPQ. It again. Angle BCQ and triangle BCQ equals to angle BPQ and triangle BPQ. They are both equal to 45 degrees and therefore they are equal to each other. In triangle BQP, this angle equals to 45 degrees, this angle equals to 15 degrees, 45 degrees plus 15 degrees is 60 degrees, and therefore this quadrant angle must be equal to 120 degrees in its size, according to the rule that the sum of the angles in the triangle is equal to 180 degrees. So this quadrant angle must be equal to 120 degrees in its size. So actually, those two angles, they are both equal to 120 degrees and therefore they are equal to each other. So actually, this is angle BQC, and I have BQC. And it is equal to this angle, this is actually angle PQB. Entire BPQ. Again, I have found out that angle BQC entire BCQ is equal to angle PQB entire BPQ. They are both equal to 120 degrees and therefore they are equal to each other. This is side QB. Side QB is the current side that belongs to both triangles. Side QB belongs to triangle PQB and side QB belongs to triangle BQC. So you can write down that BQ equals to itself is a common side that belongs to both triangles. Again, BQ equals to itself is a common side that belongs to both triangles. And finally, those two angles are both equal to 15 degrees and therefore they are equal to each other. So actually, this is angle QBC. It's angle BCQ and it is equal to this angle, that is angle PBQ. It's angle PQB. And again, angle QBC, it's angle BCQ equals to angle PBQ, it's angle BPQ. They are both equal to 15 degrees and therefore they are equal to each other. So we actually found out that those two angles and the side that is included between those two angles is actually side QB. This angle PQB are correspondingly equal to those two angles. The side that is included between those two angles is also side QB. This triangle QBC, and therefore those two triangles can go into each other according to angle side angle rule. We have those two angles and the side that is included between those two angles in triangle PQB are corresponding equal to those two angles and the side that is included between those two angles. This triangle PQC, and therefore this triangle BQC, and therefore those two triangles can go into each other according to angle side angle rule. So I write it down. I should hold on that triangle BQC congruent, this is the sign of congruent to triangle BPQ according to angle side angle rule. And for the fact that those two triangles can go into each other, we derive that PB equals to BC. This is side PB is equals to side BC. PB equals to BC. PB and BC, the corresponding sides, because PB is located in front of this angle is equal to 120 degrees in size, and BC is also located in front of this angle is equal to 120 degrees in its size. And again, BC is the corresponding size of BP. BC is triangle BQC is the corresponding size of
side PB, in this side PBQ. So while those two corresponding sides are equal to each other, those two corresponding sides are equal to each other, according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore those two corresponding sides, that is to say BP, BC, must be also equal to each other at their lengths. So PB equals to BC. But according to what is given as the equation, PB equals to 5. So I can write that PB equals to 5. And for this equation, 5 equals to BC, 5 equals to PB equals to BC. We will derive that BC also equals to 5 units in its length. So here, this is side BC, equals to 5 units in its length. Our test is to find out the of this square ABCD. What is the of square ABCD? I'm sure you know that the of any square equals to the length of one side squared. Therefore it will be equal to the length of BC squared. So the length of square ABCD equals to BC squared. BC is 5, therefore BC squared is 5 squared. 5 squared is 25. So in total we should know that the area of square ABCD is equal to 25 squares in its size. And again, I should know that the area of this square ABCD is equal to 25 squares in its size. So we finished with the first method. The next step I will present to you how to find out the area of this square ABCD according to a second method. You know that diagonal DB bisects angles, the angles of the square. So this angle, the first half of angle ADC must be equal to 45 degrees in its size. This is the second half of angle ADC is equal to 45 degrees in its size. So this angle equals to 30 degrees, and therefore this missing angle must be equal to 15 degrees in its size. Because 30 plus 15 is 45 degrees. It is the size of the second half of angle CDA.
diagonal DB bisect angle ABC. So this is the first half, this is equal to 45 degrees in size. And this is the second half, this is also equal to 45 degrees in size. So this angle equals to 30 degrees, and this angle must be equal to 15 degrees in size, because 15 plus 30 is 45. That is the size of this second half of angle ABC of square ABCD. So this angle must be equal to 15 degrees in size. So in the next step, we'll focus on this triangle BDP. Triangle BDP, this angle equals to 30 degrees. This angle equals to 15 degrees. 30 degrees plus 15 degrees is 45 degrees. Therefore, this third missing angle must be equal to 135 degrees in size, according to the law that the sum of the angles in the angle is equal to 180 degrees. 45 degrees plus 135 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we'll do construction. That is to say, we'll draw a circle around square ABCD in such a way that point A will be the center of the circle that we draw, and AB will be the radius of the circle. So AB, we define AB as X. AD is also X, of course. Repeat again. We do a construction, we draw a circle around square ABCD in such a way that point A will be the center of the circle that we draw, and the area of the circle, and the radius of the circle will be equal to X, that is the side length of square ABCD. Okay, this is the circle that we draw around square ABCD. Point A is the center of the circle, that is vertex A of square ABCD. AB equals to AD, that is actually the radius of the circle is equal to X. So the side length of square ABCD is also the radius of this circle. So here we draw constructing a circle around square ABCD. It is ready to prove that the circle that we draw must pass for vertex B and vertex D of this square ABCD. I will not prove it, that it is very easy to prove that vertex B and vertex D must pass for the center, for the circle. Again, vertex B and vertex D must pass for this circle that we draw here. Okay. So we already found out that angle BPD is equal to 135 degrees in its size. This is angle BPD that equals to 135 degrees in its size. This is angle DAB. What is the size of the big angle DAB? Angle BAD or square BCD of course equals to 90 degrees in size. We know that the sum of the angles around any point is equal to 360 degrees. Therefore, this missing angle, so 90 degrees plus the missing angle in total must be equal to 360 degrees according to the rule that I mentioned, and therefore this missing angle must be equal to 270 degrees in its size. So this is center angle DAB. Is equal to 270 degrees in its size. Center angle DAB subtend or code DB. Again, the big center angle DAB subtend or code DB. This is angle DPB. Angle DPB also subtend on the same code called DB. So here I present to you Rule 13, and we'll implement Rule 13 in our drawing. According to Rule 13, a center angle is twice as large as the peripheral angle is subtended on the same chord. In the drawing, we have a circle. This is center angle, and this is peripheral angle ACB that's subtended on chord AB, and this is equals to theta degrees in size. This is center angle AOB. It's subtend on the same chord called AB. According to this Rule 13, the center angle AOB must be equal to twice as the peripheral angle ACB that's subtend on the same chord called AB. A peripheral angle ACB equals to theta, and therefore the center angle AOB must be twice as large as the peripheral angle, this peripheral angle that's subtend on the same chord called AB. And therefore the size of center angle AB must be equal to 2 theta. So if you have a center angle and a peripheral angle that's subtend on the same chord, the size of the center angle must be twice as large as the size of the peripheral angle that's subtend on the same chord, in this case called AB. This is center angle DAB. Is equals to 270 degrees in its size. This is angle DPB. This is equals to 270 degrees over 2 is 135 degrees. So peripheral angle DPB obeys to Rule 13. Why? Because it is equal to 135 degrees. That is half of the size of center angle DAB. The substance on the same chord called DB. And because of the fact that angle DPB obeys to Rule 13, it must be a peripheral angle. Again, because of the fact that angle DBP is equal to 150 degrees in its size, obeys to Rule 13, it must be a peripheral angle. Okay? So, angle DPB is a peripheral angle. Note that all the three vertices of a peripheral angle must lie on the circle. Vertex D lie on the circle. Vertex D of peripheral angle DPB lie on the circle. Vertex P also lie on this circle. So vertex P must lie on this circle. That is to say, the circle that we drew must pass through point P. Again, the circle that we drew must pass through point P because angle DPB is a peripheral angle and all the vertices of peripheral angle must lie on the circle. So this circle must pass through point P. Okay? So in the next step, we'll join points A and P together by a straight line. Point A is the center of the circle, point P is the point of the circle itself, point P is the point of the circle itself, therefore AP is of course the radius of the circle that is equal to x according to our definition. So in the next step, I will copy triangle ABP in a new page, and we will analyze this triangle ABP. This is angle ABP. Angle ABP total cost to 45 degrees plus 15 degrees is 60 degrees. So actually, this is triangle ABP that I formed from the original drawing. Repeat again, this is angle ABP that is equals to 60 degrees in size. AB equals to AP equals to X. Again, AB equals to AP equals to X. So in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. But this angle equals to 60 degrees, and therefore this angle must be also equal to 60 degrees in size. So in this triangle ABP, 60 degrees plus 60 degrees is 120 degrees, and therefore this furthest angle must be equal to 60 degrees in size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So all the angles of this triangle ABP now equal, each of them is equal to 60 degrees, and therefore quadrilateral ABP is an equilateral triangle. And triangle ABP is an equilateral triangle. We know that all the sides of any equilateral triangle are equal to each other. So in equilateral triangle ABP, BP equals to AB. EP equals to AB. BP equals to AB. But according to what is given us in the question, BP equals to 5. So can I do the BP equals to 5? And for this equation, AB equals to BP equals to 5. We derive that AB also equals to 5 units in its length. AB equals to 5. Side AB equals to 5. Our test is to find out this curve for ABCD. Now, pi squared equals to the length of one side squared. So it will be equal to the length of one side AB squared.
AB is 5, so 4AB squared is 5 squared, that is 25. And then we found out that the of the square ABCD is equal to 25 square units in size. So we finished with the second method. In the next step, I'll present to you how to find out the of the square ABCD according to the third method. In the third method, we find the side AB of square ABCD. This side is x. Therefore, side AD also must be also equal to x, because all the sides of a square are equal to each other. This angle is a right angle. So we have here the right triangle DBA. This right triangle DBA, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle ADB, DB squared, that is the square of the hypotenuse, must be equal to AD squared plus AB squared. Write it down. In the right triangle DBA, here by PT is a proportion from Pythagoras theorem. TB squared, that is the square of the hypotenuse, is equal to AB squared plus AD squared. DB is the missing side, so leave it as it is, so it is DB squared equals to AB squared. AB is x, therefore AB squared is x squared plus AD squared. AD is x, therefore AD squared is x squared. So in total, we should find out that DB squared equals to x squared plus x squared, that is 2x squared. DB squared equals to 2x squared. Here we take a look out of this equation. I get that DB is equal to the square root of 2 times the square root of x squared. The square root of x squared is x. In total, we should find out that DB equals to the square root of 2 times x units in its length. This is the hypotenuse DB, that is equals to the square root of 2 times x units in its length. Diagonal DB of square ABCD bisect the angles of the square. Diagonal DB bisect the angle ABC. So this angle, the first half of angle ABC, is equals to 45 degrees in size. But this angle equals to 30 degrees, and therefore this angle must be equal to 15 degrees in its size. Likewise,
So here we have triangle BDP. This is triangle BDP. This angle equals to 15 degrees. This angle equals to 30 degrees. 15 degrees plus 30 degrees is 45 degrees, and therefore this third angle must be equal to 135 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. The next step, we'll implement the law of sines in this triangle, triangle DBP. Repeat quickly on the law of sines. The law of sines is true in any triangle. This is triangle ABC that could be any triangle. Side AB equals to C units in its left, side AC equals to B units in its left, side BC equals to A units in its left. Capital A is the size of this angle BAC, capital B is the size of this angle ABC, and capital C is the size of this angle ACB. According to this law, the law of sines, the following equation is true. That A over sinus A equals to B over sinus B equals to C over sinus C. And again, A over sinus A equals to B over sinus B equals to C over sinus C. A over sinus A equals to B over sinus B equals to C over sinus C. So we can implement the law of sines in this triangle, triangle DBC. In triangle DBC, according to the law of sines, it's given us the question that side BP equals to 5 units in its length. So in this triangle DBP, according to the law of sines, we get that 5 over sinus 30 degrees equals to the square root of 2 times x over sinus 135 degrees. Again, 5 over sinus 30 degrees is equal to the square root of 2 times x over sinus 135 degrees. Okay, again in triangle BDP, according to the law of sines, the following equation is told that 5 over sinus 30 degrees equals to the square root of 2 times x over sinus 135 degrees. That is 5 over sinus 30 degrees. Sinus 30 degrees is equal to 1/2. It is equal to the square root of 2 times x for sinus 135 degrees. Sinus 135 degrees is equal to the square root of 2 over 2. So in total, we shall find that 5 over 1/2 equals to the square root of 2 times x or square root of 2 over 2. 5 over 2 is 5 over 1/2 equals to 10. And is equals to the square root of 2 times x or the square root of 2 over 2. Here we move 2 to the numerator and square root of 2 to the denominator, and we get that this expression total equals to the square root of 2 times x times 2 to the square root of 2. So if we found out that 10 equals to the square root of 2 times x times 2 square root of 2. Here square root of 2 in the numerator, square root of 2 in the denominator, so square root of 2 will get cancelled. And we're left only with 10 equals to 2x. 10 equals to 2x, we will divide this equation by 2. And finally get that x equals to 10 over 2 is 5. X equals to 5. So AD equals to 5, AB is also equals to 5. So the area of square ABCD is equal to the length of one side squared. The length of one side is 5, so it is 5 squared. 5 squared is 25. So totally we found out that the area of square ABCD is equal to 25 square units in size. So we finish with the third method. The next step on some of the lecture. We start with the first question, of course. In the first question, our task is to find out the area of this green shape. So in the drawing, we have a circle that is described by this triangle, triangle ABC. We know that AB equals to 6 units in length, side AC of triangle ABC equals to 7 units in length, side BC equals to 9 units in length. Again, our task is to find out the area of this green shape. So first of all, we define this angle ACB as theta, and implemented the law of cosines in this triangle, triangle ABC. According to the law of cosines that is true in any triangle, this is triangle ABC that could be any triangle. Side AB equals to A units in its length, side AC equals to B units in its length, side BC equals to C units in its length. This is angle BAC that equals to theta degrees in its size. This triangle ABC that could be any triangle, cosine theta equals to A square plus B square minus C square, over 2 times A times B. Again, cosine theta equals to A square plus B square minus C square, over 2 times A times B. So implemented the law of cosines in this triangle ABC. According to the law of cosines, this triangle ABC. Cosine theta equals to 7 square plus 9 square on 6 square over 2 times 9 times 7. It again, a triangle ABC, turned into the law of cosines. We get that cosine theta equals to 7 square plus 9 square over 3 square on 6 square over 2 times 7 times 9. 7 square is 49 plus 9 square is 81 on 6 square that is 36 over 7 times 9 is 63. 63 times 2 is 126. 49 plus 81 is 130. This is 130 minus 36 over 226. 130 minus 36 is 94 over 226. 94 over 226 is equals to 0.7169. And so in total we should find out that cosine theta equals to 0.7169. We would like to find out the value of theta itself. In order to find out the value of angle theta itself, we'll operate the opposite function of cosine, that is arc cosine, on the result of cosine theta, that is 0.7169, and this way we get the value of angle theta itself. So arc cosine of the result of cosine theta, that is 0.7169, equals to theta. And you can find in any scientific calculator that arc cosine of 0.7169 is equal to 40 degrees, 0.362 degrees. 40 degrees, 40.632 degrees. So theta equals to 40.62 degrees in its size. And therefore 180 degrees minus theta must be equal to 180 degrees minus 40.632 degrees, that is 139.632 degrees in its size. In the next step, we define center of this circle. This point is point O. We define the point of tendency of tangent BC with this circle. This point is point L. We define the point of tendency of tangent B with this circle. This point is point Q. And we define the point of tendency of tangent AC with this circle. This point is point P. We define the radius of this circle as R. We join points O and L together by certain time. Point O is the center of the circle. Point L is the point of the circle itself. Therefore, OL is the radius of the circle is equals to R. The radius of L is equals to R. The radius of L is drawn to point L. That is the point of tendency of tangent BC with this circle. And whenever your that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius LO. If BC is perpendicular to LO, which means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to 1, 1. The next step, we join points O and P together by certain OP is the radius of the circle that equals to R. According to 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees in size. When doing this construction, we created quadrangle OPCL. In quadrangle OPCL, we know that the sum of the angles in any quadrangle is equal to 460 degrees. So in quadrangle OPCL, 90 degrees plus 90 degrees, that is 180 degrees, plus theta plus the angle POL, in total must be equal to 460 degrees according to the rule that I mentioned. So if you found out that in quadrangle OPCL, in total 180 degrees plus theta plus the missing LOP in total must be equal to 460 degrees. Here we subtract 180 degrees from this equation and found out that 460 degrees minus 180 degrees is 180 degrees. This side of the equation we have theta plus the missing LOP equals to 180 degrees. Here we subtract the theta from this equation. We subtract the theta from this equation and find out that the missing LOP equals to 180 degrees minus theta. this is the missing angle LOP, this is equals to 180 degrees minus theta in its size. Okay, we found out that 180 degrees minus theta equals to 139.632 degrees. So you can write here that 180 degrees minus theta, this is the size of the angle LOP, is equal to 139.632 degrees in its size. We have a special formula that says that they are of any triangle this is the triangle ABC, or they are of any triangle equals to the square root of S times S minus A times S minus B times S minus C. S is the semi-perimeter of the triangle, the perimeter over 2. So this triangle ABC, the semi-perimeter equals to 6 plus 7 plus 9 over 2. It's actually 11. And here, A, B, and C are the side lengths of the triangle. A, B, and C are the side lengths of the triangle. In this case, A equals to AB to the 6, B equals to AC to the 7, and C equals to BC, that is 9. So the triangle ABC equals to the square root of S is 11, times S minus A. S is 11, A is 6, so 11 minus 6 is 5, times S minus B. S is 11, B is 7, so 11 minus 7 is 4, times S minus C. S is 11, C is 9, so 11 minus 9 is 2. So in total, the triangle ABC is equals to the square root of 11 times 5 times 4 times 2. The square root of 4 is 2, so took 4 out of this root. And she found out that the triangle ABC in total equals to 2 times inside the root we have to leave 11 times 5 times 2. 11 times 5 is 55, 55 times 2 is 110. So in total she found out that the triangle ABC, we have this triangle ABC is equal to 2 times square root of 110. We know that the area of any triangle that blocks a circle, the area of any triangle that blocks a circle, like this triangle ABC that blocks this circle, is equal to S times R. S is the semi-perimeter of the triangle that blocks the circle. R is the radius of the circle that is described by triangle ABC. We only found out that the semi-perimeter S of triangle ABC is 11. R is the radius of the circle that is described by triangle ABC, that is the missing side. And we just right now found out that the triangle ABC equals to 2 times square root of 110 square root in its size. So in total we found out that 2 times the square root of 110 equals to 11 times R. Here we divided this equation by 11 and finally found out that the radius R of this circle that is described by triangle ABC is equal to 2 times square root of 110 over 11. 2 times square root of 110 over 11 is equal to 1.907 units in its length. So the radius of this circle R equals to 1.907 units in its length. Our task is to find out the area of this green shape. So what is our task is to find out the area of this green shape. So what is the area of this green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of quadrant LOPC minus the area of this sector OPL. What is a sector? A sector is a portion of a circle enclosed by 2 radii and the arc between them. filling in. This is sector A or B. This is a portion of a circle. It is closed by 2 radii and RKB between them. So the area of this sector equals to pi r squared. That is the radius of the circle that consists sector A or B times the 2 radii defined as the length of the sector times the angle between the length of the sector that is theta or 360 degrees. Repeat again. The area of sector AB equals to pi r squared times theta or 360 degrees. Okay. But before we continue, we actually implemented all 2 in our drawing. I can click on rule 2. According to rule 2, the lengths of 2 tangents from a common standpoint to a circle are equal. In the drawing circle, this is the common standpoint point P. For this common standpoint point P, we have 2 tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can implement rule 2 in our drawing. What we put in our drawing here we defined line segment LB as A. So we'll focus on this common standpoint point B. From this common standpoint point B, we have 2 tangents to this circle, tangent BL and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BL equals to BQ. But BL is A, therefore BQ must be also equal to A units in its length. AB is 6, BQ is A. Therefore AQ equals to AB minus AQ. AQ equals to AB minus BQ. So AQ equals to AB, that is 6, minus BQ, that is 8. So in total, AQ equals to 6 minus 8. Then we implemented rule 2, the common standpoint point F. On the common standpoint point A, we have 2 tangents to this circle, tangent AQ and tangent AP. And according to rule 2, they are equal to each other. That is to say, AQ equals to AP. But AQ is 6 minus 8, therefore AP must be also equal to 6 minus 8 in its length. LC equals to BC, that is 9, minus BL, that is 8. So in total, LC equals to 9 minus 8. The next step, we focus on this common standpoint point C. For this common standpoint point C, we have 2 tangents to this circle, tangent CL and tangent CP. And according to rule 2, they are equal to each other. That is to say, CL equals to CP. But CL is 9 minus 8, therefore CP must be also equal to 9 minus 8 in its length. AC in total is 7, according to what is given as the question. Side AC of triangle BC equals to 7 units in its length. AC consists of 2 line segments, AP and PC. So AC equals to AP plus PC. AC equals to AP, that is 6 minus 8, plus PC, that is 9 minus 8. So in total, AC equals to 6 minus 8 plus 9 minus 8. AC equals to 6 plus 9 is 15, minus 8 minus 8 is minus 2A. So AC in total equals to 15 minus 2A. But AC is 7, so we substitute AC by 7. We found out that 7 equals to 15 minus 8. Here we subtracted 7, and then we added 2A to this equation simultaneously, and finally found out that 2A equals to 8. Here we divided this equation by 2, and finally found out that A equals to 8 over 2 is 4. So A equals to 4, A equals to 4. 6 minus 8, 6 minus 4, that is 2. 6 minus 8 is 2. 9 minus 8 is 9 minus 4, that is 5. LC equals to 9 minus 8, that is 5. Repeat again. We only found out that there of this green shape must be equal to there of quadrant OLCP minus there of this sector LOP. There of the green shape is equal to there of quadrant POLC minus there of sector POL. In the next step, we join point C and O together by straight line. Again, we join point C and O together by straight line. By joining point C and O, we create those two right triangles, triangle OPC and triangle OLP. Actually, quadrilateral LOPC consists of those two shapes, those two right triangles. And therefore, the area of quadrilateral LOP must be equal to the area of the first shape. The area of quadrilateral LOP must be equal to the sum of the areas of the that it consists of. That is to say, it must be equal to the area of the first shape, that is the right triangle POL, the right triangle OPC, plus the area of the second shape that it consists, that is the right triangle LOC. So the area of quadrilateral OPC must be equal to the area of the first shape, that is the right triangle OPC, plus the area of the second shape, that is the right triangle OLC. Minus the area of sector POL. According to the formula that I presented to you a couple minutes ago, the area of this sector LOP must be equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the circle to the 139.632 degrees or 360 degrees. So total, the area of sector POL equals to pi r squared times the angle between the legs of the circle, that is 139.652 degrees or 360 degrees. What is the area of right triangle OPC? The area of this right triangle OPC equals to the base OP times the height PC over 2. The area of triangle OPC equals to the base OP times the height PC over 2. Plus the area of this right triangle LOC. The area of this right triangle LOC equals to the base LO times the height LC over 2. Again, the area of the right triangle OLC equals to the base OL times the height LC over 2. OP is R, PC is 5 divided by 2. And OP is R, PC is 5 divided by 2. So here OL is R, LC is 5 divided by 2. OL is R, LC is 5 divided by 2. The area of sector POL equals to the area of this expression. Actually, the radius R is 1.907. So pi r squared is pi times 1.907 squared times 139.632 degrees over 360 degrees. So in total, the area of this big expression equals to 4.387 square inches in size. So in total, we should find out that the area of this sector POL equals to 4.387 square inches in size. 4.387 square inches in size. Here we have 5r over 2 plus 5r over 2 is 5r minus 3.87. R is 1.907 and therefore 5r is 5 times 1.07, that is 9.535 minus 4.387. 9.535 minus 1.387 equals to 5.184 square inches in size. So we should find out that the area of this green shape, that is the area that we are looking for in this question, is equal to 5.148 square inches in size. So we finish with the first question. In the next step, I presented to you actually the second question, and so we'll repeat on the solution of the second question we solved the second question in three different methods. So I'll repeat on the solution of the second question in three different methods. Our task in the second question is to find out the area of this square ABCD. In the drawing of square ABCD, DB is the diagonal of this square ABCD. In addition, you know that this is angle BDP equals to 30 degrees in size. This is angle QBC, this is also equals to 30 degrees in size. This is line 7BP, this is equals to 5 units in its length. Here our test is to find out the area of this square ABCD. So first of all, we know that the diagonals of a square bisect the angles of the square. Again, the diagonals of a square bisect the angles of the square. Diagonal DB of square ABCD bisect the angle ABC. So the first half is 45 degrees and the second half is also 45 degrees. So this angle equals to 30 degrees. Therefore, this missing angle must be equal to 15 degrees in size because the second half in total is 30 degrees plus 15 degrees, that is 45 degrees. So this missing angle must be equal to 15 degrees in its size. So likewise, that one will be D bisect angle ADC. So the first half is 45 degrees and the second half is also 45 degrees, but this angle equals to 30 degrees and therefore this missing angle must be equal to 15 degrees in its side, because in total 30 degrees plus 15 degrees is 45 degrees. This is the side of this second half of angle ADC of square ABCD. So this missing angle must be equal to 15 degrees in its size. In the next step, we draw an angle bisector from point C of angle DCB. So this is the angle bisector. Angle bisector bisect angle DCB. So this angle equals to 45 degrees, and this angle also equals to 45 degrees according to our construction. In the next step, we extended line 7DP until it touches the angle bisector. It touches the angle bisector at this point, so when you find the touching point with the extended side DP with this angle bisector, this point is point Q. When doing this construction, you remember triangle DQP. In triangle DQP, 15 degrees plus 45 degrees is 60 degrees, and therefore this part missing angle must be equal to 120 degrees in its side. According to the rule that says that the sum of the angles in a triangle is equal to 180 degrees. In the next step, we join points B and Q together by a straight line. By joining points B and Q, create a triangle BQC. Angle bisector DB bisect angle ABC into two halves. The first half is 45 degrees. This is the second half. This is the second half. That is also equals to 45 degrees in size. 15 degrees plus 15 degrees is 30 degrees, and therefore this missing angle must be equal to 15 degrees in size, because 15 times 3 is 45. That is the size of the second half of angle ABC, square ABCD. So this missing angle must be equal to 15 degrees in its size. In the next step, we prove that triangle BQC congruent to this triangle DQC, hold that those two triangles congruent to each other according to side angle side rule. So why those two triangles congruent to each other? First of all, BC equals to DC. both the sides of a square that are equal to each other, and therefore they are equal to each other. In addition, those two angles are both equal to 45 degrees, and therefore they are equal to each other. And finally, side QC equals to itself. It is a common side that belongs to both triangles. So we can write down that QC equals to itself. So in total, we should know that those two sides and the angle that is equal between those two sides in triangle BQC, this triangle BQC, are corresponding equal to those two sides and the angle that is equal between those two sides in this triangle BQC. And therefore, those two triangles can run into each other according to side angle side rule. And again, I should remember that triangle BCQ can run to triangle EQC according to side angle side rule. And from the fact that those two triangles can run to each other, we derive that those two angles must be also equal to each other and their sizes according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other and their sizes. So, angle CDQ is equal to the corresponding angle QBC, according to the rule I mentioned. And angle CDQ equals to 15, so I think that angle CDQ equals to 15, and for this equation, 15 equals to angle CDQ equals to angle QBC, we derive that angle QBC is also equal to 15 degrees in its size. Angle QBC is also equal to 15 degrees in its size. So, in the next step, I copied triangle BDP in a new page and implemented rule 8 in this triangle BDP. So actually, this is triangle BDP, this is according to the original drawing. This triangle BDP, this angle equals to 15 degrees, this angle equals to 30 degrees. Those three angles inside triangle BDP are of course defined as triangles. This angle BPQ is an angle because it is located outside triangle BPD. According to rule 8, next door angle of a triangle is equal to the sum of the two intervals that are not adjacent to it. This is triangle ABC that could be any triangle. Those triangles alpha, beta, and gamma are defined as intervals. This is angle 8 that is defined as an extraangle because it is located outside triangle ABC. According to this rule 8, the size of this interval E is equal to the sum of the two intervals that are not adjacent to it. Angle gamma is definitely adjacent to angle E. The two intervals that are not adjacent to it are those two angles, alpha and beta. And therefore, according to this rule 8, angle E equals to alpha plus beta. That is the sum of the two intervals that are not adjacent to angle E. We can actually implement rule 8 in our drawing. Because in our drawing, we have triangle BDP, BPQ, angle BPQ is the extraangle. According to rule 8, the size of the extraangle BPQ equals to the sum of the two intervals that are not adjacent to it. Those are the two intervals that are not adjacent to it. So BPQ equals to 15 plus 30, that's 45. So this is the missing angle BPQ, that equals to 45 degrees in size. So it's angle PQB. This angle equals to 15 degrees, this angle equals to 45 degrees, 15 plus 45 is 60. This first angle must be equal to 120 degrees inside according to the rule that the sum of the angles in the angle is equal to 120 degrees. Likewise, in this angle BQC, this angle equals to 15 degrees, this angle equals to 45 degrees, 15 degrees plus 45 degrees is 60 degrees, and therefore this first angle must be equal to 120 degrees in size according to the sum rule. The next step, we prove that those two triangles can go into each other according to angle side angle rule. So all those two triangles can go into each other. First of all, those two angles are both equal to 120 degrees and therefore they are equal to each other. In addition, BQ is a common side that belongs to both triangles, so we can write down that BQ equals to itself is a common side that belongs to both triangles. And finally, those triangles are both equal to 15 degrees and therefore they are equal to each other. So we should find out that those two angles and the side that is included between those two angles, that is side BQ and triangle, this triangle PQB, are corresponding equal to those two angles and the side that is included between those two angles in this triangle BQC, and therefore those two triangles can go into each other according to angle side angle rule. Again, if you remember that triangle BQC can go into triangle BPQ according to angle side angle rule. And for the fact that those two triangles can go into each other, we derive that PB equals to BC. PB equals to BC. PB and BC are defined as corresponding sides because both of them are located in front of the angle that is equal to 120 degrees in size. So those two sides are equal to each other according to the rule that corresponding sides of congruent triangles are equal to each other. Those two triangles can go into each other, and therefore the two corresponding sides BP, let's say to say BC and BP, must be also equal to each other in their lengths. Again, BP equals to PB equals to BC, but BP is 5 according to what is going to the equation. So we can write down that BP is 5, and from this equation 5 equals to PB equals to BC. We write that BC also equals to 5 units in its length. This is side BC, this equals to 5 units in its length. Our task is to find out the square ABCD. You know that the aeroplane square equals to the length of one side squared. Therefore, the square ABCD must be equal to the length of one side, that is the length of BC squared. The square ABCD must be equal to the length of one side squared, that is to say BC squared. BC is 5, therefore BC is 5. Therefore BC squared is 5 squared, that is 25. So in total we found out that the area of this square ABCD is equal to 25 square units in its size. So we finish with the first method. In the next step, I'll present to you how we found out the area of the square ABCD according to the second method. I'll repeat on the solution of the second method how to find out the area of the square ABCD. So I'll not repeat on the things that were already done here. Double DB, dissect the angles of those two angles of square ABCD. Therefore, this angle equals to 45 degrees. the second half is also 45 degrees, and therefore 30 degrees plus 15 degrees is 45 degrees. Likewise, diagonal DB by rectangle ABC. So this angle, the first half is 45 degrees, and the second half is also 45 degrees, but this is the second half of angle ABC is equal to 45 degrees, but this angle is 30 degrees, and therefore this angle must be equal to 15 degrees in its size. So in triangle BDP, 15 degrees plus 30 degrees is 45 degrees, and therefore this first angle must be equal to 135 degrees in size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we did the construction, that is to say, we draw a circle around square ABCD in such a way that point A will be the center of the circle that we draw, and AB will be the radius of the circle. So we define AB as x, therefore AD is also equal to x. So actually this is the circle that we draw around square ABCD. So as I mentioned before, point A, vertex A of square ABCD is the center of this circle. AB equals to AD, above the radius of the circle. Actually the radius of this circle is also the side length of this square ABCD. We define the radius AB is x, so AD is also equals to x, that is the radius of this circle. This is triangle DAB. Triangle DAB. This is triangle DAB. Triangle DAB. Subset of called DB. Again, triangle DAB. Subset of called DB. This is one angle of square ABCD. This is of course equal to 90 degrees. We know that the sum of the angles around any point is equal to 360 degrees. This angle equals to 90 degrees, and therefore this missing angle must be equal to 230 degrees, because 230 degrees plus 90 degrees, it is 360 degrees, that is the sum of the angles around any point and also around point A. Set angle DAB is equal to 270 degrees in size, and it's subset of 4 dB. This is angle DPB equals to 135 degrees in size. Angle DPB equals to 135 degrees in size. So here we can implement rule 13. According to rule 13, the center angle is twice as large as the peripheral angle subtended on the same chord. The one in a circle, this is peripheral angle ACB. It's subtended on 4 dB, and it is equal to 30 degrees in its size. Likewise, we also center angle AOB, it's subtended on the same chord called AB. And because of the fact that this peripheral angle and this center angle subset on the same chord AB, the center angle AOB must be twice as large as the peripheral angle ACB. Peripheral angle ACB equals to theta, and therefore center angle AOB must be equal to 2 theta. Read again. Center angle DAB subtended on 4 dB and equals to 230 degrees in its size. This is again DPB, it's subtended on the same chord called dB, and it is equals to half of this angle. Half of the center angle dB, this is 270 degrees over 2 is 135 degrees. And because of the fact that angle angle DPB that subtend on the same chord called VB, exactly like the set angle VB. So it obeys to rule 13. That is to say, we have peripheral angle that subset on the same chord called DB, exactly like set angle DB. They are both subset on the same chord called DB. And the size of the this angle is half of the size of this angle. 270 degrees over 2 is 135 degrees. So set angle DB is twice as large as this angle DBB. So because of the fact that angle DPB obeys to rule 13, it must be a peripheral angle. And again, because of the fact that angle DBB obeys to rule 13, it must be a peripheral angle. So DPP is a peripheral angle. We know that all the three vertices of peripheral angle, any peripheral angle, lie on the circle. Point D lie on the circle, point B lie on the circle, point P must lie on this circle. That is to say, the circle that we drew must pass for point P. Okay? So point A is the center of the circle, point P is the point of the circle itself, therefore AP is the radius of this circle that is equal to X according to our definition. So in the next step, I copied triangle ABP and we analyze this triangle ABP. This is angle ABP, this equals the total to 45 degrees plus 15 degrees is 60 degrees. So I copy triangle ABP in new page and analyze this triangle ABP. This is triangle ABP that I copied from the original domain. So we found out that angle ABP equals to 60 degrees in its size. 45 degrees plus 15 degrees is 60 degrees. Those two sides are equal to each other. Both of them equals to X and therefore they are equal to each other. In front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. But this angle equals to 60 degrees and therefore this missing angle must be also equal to 60 degrees in its size, according to the dimensions. In front of equal sides in the triangle, there are equal angles. So in triangle ABP, 60 degrees plus 60 degrees is 120 degrees. Therefore, this missing angle must be equal to 60 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Triangle ABP is three angles, that is of them is equal to 60 degrees. Three equal angles, and therefore angle ABP is an equilateral triangle. But we know that all the sides of any equilateral triangle are equal to each other. That is to say, AB equals to BP. In equilateral ABP, AB equals to BP. But according to what is given as the equation, BP equals to 5. And according to the equation, AB equals to PB, AB equals to BP equals to 5, and now that AB is also equal to 5 units in its length. This is side AB, is equals to 5 units in its length. You know that the area of any square equals to the length of one side squared, that is to say, so it is the length of side AB squared. The area of square ABCD equals to the length of side AB squared. AB is 5. So AB squared is 5 squared, that is 25. So according to the second method, we found out that the area of the square ABCD equals to 25 squares in its size. So we finish with the second method. In the next step, I repeat on the third solution. I repeat on the solution what is the area of the square ABCD according to the third method. Again, diagonal DB bisect angle ABC of square ABCD. So this angle equals to 30 degrees, and therefore this missing angle must be equal to 15 degrees because it is the second half of angle ABC. This is 45 degrees. Okay. This gives us the question that this angle equals to 30 degrees in its size. So triangle DBP, 30 degrees plus 15 degrees is 45 degrees. Therefore, this missing angle must be equal to 135 degrees in its size, according to the rule that says that the sum of the angles in a triangle is equal to 180 degrees. This angle equals to 90 degrees, because it is one angle of square ABCD. We define AB as x. Therefore, AD must be also equal to x because all the sides of any square are equal to each other. In the next step, we implement the Pythagoras theorem with this triangle ABD. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle ADB, according to the Pythagoras theorem, DB squared, that is the square of the hypotenuse, equals to AD squared plus AB squared. Okay, again, triangle ABD, according to the Pythagoras theorem, DB squared, that is the square of the hypotenuse, equals to AB squared plus AD squared. DB is the missing side, the hypotenuse DB is the missing side, so we have this it is. So DB squared equals to AB squared. AB is x, therefore AB squared is x squared plus AD squared. AD is also x, so AD squared is x squared. So in total, DB squared equals to x plus x. X plus x is to x squared plus x squared. X squared plus x squared is 2x squared. So in total, DB squared equals to 2x squared. Here we took a root out of this equation, and we found out that DB, the missing hypotenuse DB, equals to the square root of 2 times the square root of x squared. The square root of x squared is x. So in total, DB equals to square root of 2 times x. DB, and hypotenuse DB equals to the square root of 2 times x units in its length. According to what is given as the equation, PB equals to 5 units in its length. In the next step, we implemented the law of sines in this triangle DBP. The law of sines is true in any triangle. This is triangle ABC that could be any triangle. Side AB, triangle ABC equals to 3 units in itself, side BC equals to 1 unit in itself, side DC equals to B units in itself. Capital A is the size of angle BAC. Capital B is the size of angle ABC, and capital C is the size of angle ACB. So according to this law, the law of cosines, the following equation is true, that A over sinus A equals to B over sinus B equals to C over sinus C. And again, in triangle ABC, the two-line triangle, according to the law of sines, A over sinus A equals to B over sinus B equals to C over sinus C. You can implement the law of sines on this triangle BDP. Triangle BDP, DB over sinus 135 degrees equals to BP over sinus 30 degrees. And again, dB over sinus 135 degrees equals to dB over sinus 135 degrees. dB is short of 2 times x, and BP is 5. So in total, if you want to know that square root of 2 times x over 135 degrees equals to 5 over sinus 30 degrees. And again, according to the law of sines in triangle BDP, 5 over sinus 30 degrees equals to the square root of 2 times x over sinus 135 degrees. Sinus 30 degrees is 1/2. Sinus 135 degrees is square root of 2 over 2. So in total, we should know that 5 over 1/2 equals to the square root of 2 times x over square root of 2 times 2. 5 over 1/2 is 10. This is equals to the square root of 2 times x over square root of 2 times 2. We move 2 to the numerator and square root of 2 to the denominator, so in total this expression equals to the square root of 2 times x times 2 over square root of 2. So 10 equals to the square root of 2 times x times 2 over square root of 2. We have square root of 2 in the numerator, square root of 2 in the denominator, so square root of 2 gets cancelled, and we have to leave 10 equals to 2x. We divided this equation by 2 and found out that x equals to 10 over 2, that is 5. X equals to 5, so AB equals to 5, AD also equals to 5. So one side of, therefore one side of square ABCD is 5. You know that the of square ABCD equals to the length of one side squared. So to actually, the length of one side is 5, so it is 5 squared. 5 squared is 25, so in total we found out that this square ABCD according to the first method is equal to 25 squares in size. So in all three methods we found out that the of this square ABCD is equal to 25 squares in size. Okay, thank you very much.